So welcome back everybody. In the last video, the last time, we talked about étale algebras, orders and fractional ideals. And today we are going to talk about isomorphism classes of fractional ideals, what we call ideal classes. Okay, let's introduce the notation that we are going to use today. It's similar to what we used in the previous video. So R is going to be always an order inside an étale Q algebra. And this étale algebra will be, we're going to denote it K. Denoted by K. Okay. And as the last time, we are going to use this I of R to denote the set of fractional ideal, the monoid of fractional ideal. Okay, so the first thing that we want to do is to turn this IR into a category. This means that we want to define a category, which we are also going to denote by IR, such that the object are precisely the fractional ideals. So what we are missing is that we need to define what are the morphisms in this category. And remember that fractional ideals are a special kind of R modules. So, well, the natural idea is to take as morphisms R linear maps, so R linear morphisms. In other words, we are going to define the morphisms between two fractional ideals, I and J, are going to be precisely the R linear morphisms between the two of them. Okay, good. So now the first question that we want to try to address is, can we get an explicit description, a nice explicit description of this home set, of these R linear morphisms? And the answer is yes. Indeed, we have the following proposition. So if you take a map between two fractional ideals I and J, let's call it phi, then phi is a multiplication by some element of the étale algebra K. Some element alpha in K. That is, more explicitly, there is a canonical isomorphism between home R I, j and the colon ideal that we defined and discussed yesterday, J colon I. Remember that this was precisely the elements X in K, such that X times I is inside J. right? And this isomorphism is the one that sends a map, let's say phi, to the corresponding element alpha as in the statement. All right, now give me a proof. Let me give you a proof. So observe that this map phi from I to j induces a unique map phi tilde from I with extended coefficient q to j tensor product, the same thing, j tensor product with q. And remember that I and j are both fractional ideals, so when you extend the coefficients you actually get the volatile algebra back, because these are both lattices, they are free abelian group of maximal rank. In other words, this phi tilde is a R-linear endomorphism of K, and K, so let me write it down, phi tilde is R-linear, and remember that we said that K can also be thought as the total quotient ring, total ring of quotients of R, okay, so it can be thought as fractions of elements of R, so an element of R divided, between quotes, by an element of a non-zero divisor of R. And so in other words, it's a K-linear map. And in particular, it is uniquely determined by the image of 1. So phi tilde of the unit element of K, which is also the unit element of R, of course. And in particular, let's say that this one is alpha. Let's call it alpha. And this proves that for every element in the fractional ideal, in the domain fractional ideal I, we have that phi of I is equal to phi tilde of I times 1 of K, which is equal to I times alpha. And this proves that phi is multiplication by this element alpha. Okay, and the second statement is a direct consequence of this fact, so there is nothing else to add. This concludes the proof of this proposition. Okay, very well. So let me give you like a quick consequence of this statement. corollary. So for every prime of R, for every prime P, we have that the RP linear homomorphisms. So when you localize R at P and you consider the RP linear morphisms between the localization of a fractional ideal of and a localization of another fractional ideal, so hom RP linear from IP to JP, this is canonically isomorphic to the colon ideal of the localizations. Okay, and here maybe this notation is a little bit imprecise, because we define the colon ideal as the elements in K that sends one ideal into the other, but now we are looking at elements between localizations. So you have to think that this is the set of elements inside the total quotient ring of the localization. And maybe you can think a little bit if this can create some small differences or not. It's like a little thought exercise. And then the second part, the second consequence of this proposition is that two ideals are isomorphic, so are linearly isomorphic. Okay, I'm gonna stop writing soon the predicts R. So I is isomorphic to J if and only if there exists an element alpha, which is a non-zero divisor in K that sends one ideal into the other by multiplication. All right? So clearly the element needs to be invertible if you want an isomorphism. So that's why we're requiring it to be a non-zero divisor. And also if you want an isomorphism here, we need to have an equality, not just an inclusion. Okay? And now we can give a name to the set of isomorphism classes of R. So we define the ideal class monoid of R. And we're going to denote it by ICM. As well, the set of fractional R ideals modulo the R linear isomorphism notion. And we also define the picker group of R which we denote by pick of R as the subset of fractional R ideal that are invertible in R, modulo the same relation of isomorphism. Okay, so let me just stress one thing. So ICM of R is a monoid and the picker group is a group, and in both cases the operation is the operation on classes induced by ideal multiplication. And I invite you to think a little bit about why this is well defined. So you take two fractional ideals I and j, you can multiply them and you get I times j. But then you can also take the classes of I and j, and I claim that the multiplication, the result of this multiplication is the class of I times j, and that this does not depend on the representative of the ideal class. In other words, if you change I by something isomorphic to I, or j by something isomorphic to j, then you will get something, the product will also be isomorphic to I times j. Okay, and also I want to stress one thing that should be clear from the definition, that the picker group is a subset, it's a subgroup actually, it's a subset of the ideal class monoid. And moreover, that we have equality if and only if every ideal is invertible in R, which we have seen in the last video at the very end, that is the same as asking that R is the maximal order of the étale algebra. Okay, cool. So let's keep studying this, the property of the ideal classes, and let me give you a lemma. So let's look for invariants of these isomorphism classes, of these ideal classes. So the first lemma is that the multiplicator ring is an invariant of an ideal class, of the ideal class. Let's prove it. Very easy proof. So we take two fractional ideals and we assume that they are isomorphic. Pick I and j fractional ideals. And let's assume that they define the same ideal class, that is I is isomorphic to j, which in other words, as we have seen, means that there exists an element, a non-zero divisor of k that sends I into j, or j into I. So let's write I equal to alpha times j. Then we have that the multiplicator ring of I, so I colon I, the set of elements that sends I inside itself, is equal to alpha j times colon alpha j. And if you look at the definition of colon ideal, you see that we can simplify the alpha from both sides, and you get j colon j, which is the multiplicator ring of j. Okay? So this concludes the proof of the lemma. So let me give an immediate consequence of this lemma first. So corollary. So let's assume that a fractional ideal I has multiplicator ring S. So yeah, take two ideals, I and j, again, fractional are ideal. And assume that, and let's denote the multiplicator ring of I with the letter S. So this is an overorder of R. And let's assume also that J is invertible in S. Okay, then the multiplicator ring of I times J is also S. Okay, so this corollary is saying that you can multiply by invertible ideals without changing the multiplicator ring. So the multiplicator ring is not just an invariant of the ideal class, it's something even more. So it's an invariant also up to multiplication by invertible ideals. And the proof, well, it's a consequence of the previous lemma, and the reason is that if J is invertible, that we have seen in the last video, that this is the same as saying that J is locally principal as ideal. And right, that is, for every P, there exists a single element, let's say alpha, which will depend on the prime, but for the moment it doesn't matter, such that the localization of J at P is equal to alpha S localized at P. And then we have that the multiplicator ring of the localizations, of the product of the localizations, so IP times JP, colon itself, is equal to alpha IP, colon alpha IP, which is equal in the same way that we proved before, that this is equal to SP. And since this holds for every prime, the construction doesn't depend on the prime P that we fixed here, this is true also globally. All right. And now, let me give you another consequence of this lemma in terms of ideal classes. So we have seen that the picker group of an order is a subset of the ideal class monoid of R, but we can actually generalize this statement, and we get that the ideal class monoid contain the disjoint union of pick of S, the picker group of S, for S any overorder of R. So where the disjoint union is taken over the overorders of R. Okay, so let's prove it. Well, it's a quick consequence of the lemma. That we just stated, together with the statement that we have seen in the last video, that was saying that if I is invertible in S, then the multiplicator ring of I is equal to S. Right? So this tells you that if you take an ideal class that is invertible, there will be a unique overorder of R such that the class sits inside the picker group. But in other words, this union is disjoint. And also every such ideal class, of course, sits inside the ideal class monoid. So we also have the inclusion. Okay. Okay, so let me say a few words about this corollary first before we move on. So I'm not going to be super precise, but what I want to say is that very often this is a very technical term, very often, we have that this inclusion is actually an equality. And as you will see soon in what I'm going to say in a minute, this is a very good news when this happens, because the picker group turns out to be quite easy to compute, while in general ideal classes are complicated. So when we are in this situation, we are very happy because we can compute the ideal class monoid very quickly. And also, if you look at the exercise sheet, you will see that we have equality if and only if R satisfies a condition, which is called being bus, a bus order after Neumann bus. So, and I invite you to look at the exercise sheets for the notion of Gorensteiness and bus and how do they relate together with respect to ideal classes. This is a very important thing, and because from the computational point of view, because as I said, very often we have an equality and this makes our life nice. But unfortunately, this is not always the case. And we want an algorithm that works in general. And don't worry, we are going to see one. But it's going to be less efficient than when we have equality. Okay? So after having said this, let's move on. Okay. So as I just said, computing the picker group is a nice thing. There is an efficient algorithm to do that. And let me say a few words about that. So we're now going to compute the picker group, and at the same time, this algorithm is also going to give us information about the unit group of R. So the elements in R that are invertible, so such that there exists another element in R, and the multiplication of the two is equal to 1. Okay, so first recall from what we said the last time, that the maximal order of K is always equal to the product of the maximal orders of the number fields that appear in the decomposition of K. So K is a product of number fields, and this decomposition into products descends to the maximal orders. Okay, and in particular, if you think a little bit, this decomposition behaves well with the notion of ideal classes. In other words, this induces a decomposition into product of the picker group of OK. So the picker group of the maximal order of the étale algebra is equal to the product of the picker group of the maximal orders of the number fields. If you have done a course in number field, you're probably very familiar with this group and with this picker group of the maximal order of a number field, because this is nothing but the class group of the number field. And typically in the literature one also see this notation, CL of R, of K. And as I said, these are called class groups. Okay, and if you dig a little bit in the literature, or maybe even in your course, you have seen that computing the class group is one of the holy grails, let's say, of number theory, of computational number theory. from the computational point of view, it's an hard problem. It's equivalent to the factorization of the discriminant. But nevertheless, there are very good algorithms that allow you to compute it. So there are very good algorithms to compute class groups. And if you want, a very good reference is the book by Henry Cohen on algorithmic number theory. There are two books that are more or less the Bible of algorithmic number theories. And yeah, I invite you to check them out if you want to see the details of the algorithms. Right, and so what I want you to keep in mind for the rest of this the lecture is that we can compute class groups. Then by just taking products, we can compute the picker group of a maximal order. So first step, keep that in mind. And now we want to do the same also for an order that is not maximal. And again, as I mentioned before, this is something that we can do. And how? Well, so for R, which is strictly contained in a maximal order, we have an exact sequence that looks like this. So the first term is the unit group of R, which is sent by a map that we're going to call iota into the unit group of the maximal order. Then there is a map which we denote by alpha that goes to the quotient of OK modulo the conductor, which we have seen already yesterday, but I'm going to remind you of the definition now. Modulo R modulo the conductor, and again units. Then there is another map beta that goes to the picker group of R, which surjects by a map which we call pi into the class group, or well, the picker group of the maximal order. Okay, so let me recall the definition of everything. So as I already said before, R star is the set of units in R, so elements of the order such that there exists another element, let's say y, again in R, not in K, in R, such that the product of the two, x times y, is equal to the unit 1. Okay, so remember that we introduced the notion of non-zero divisors. So K star was the set of non-zero divisors, but here it's similar, but we put K R instead of K. So we want also the inverse to be in R as well. Well, for OK star is the same thing. So I'm not going to write it down. Just put OK instead of R. And then the conductor, we have already seen it yesterday. Remember that it was defined as the colon ideal R colon OK. So the set of elements in K that sends the maximal order inside R. Okay. And if you look at the definition of the conductor for a second, you will realize that this is the biggest fractional OK ideal which is contained in R. This is an equivalent definition, and I invite you to think about it. So So it's an ideal that is closed by it's a lattice that is closed by multiplication by elements of OK, but it is contained in R. Okay, and then let me define the maps, iota, alpha, beta, and pi. So we have that iota is just the natural inclusion. If you take a unit in R, this will also be a unit in OK. Alpha is the projection. Maybe you have to think a little bit that it's well defined, but it's not hard. So you take a unit in OK and you send it to the class inside the quotient. Beta, this is maybe the trickiest one, the more interesting, is the map induced by the following. So it's induced by what I'm going to call here beta tilde, which is a map that goes from OK modulo the conductor unit group to the picker group of R, and this takes a class of an element, let's say U plus the ideal generated by U plus the conductor, so the class of U inside this quotient, and this is sent to the isomorphism class of the ideal, the principal ideal generated by U over OK intersected with R. So we'll use these square brackets to denote the ideal class. So sometimes I will write the symbol isomorphism, sometimes I will forget. That is the notation that I'm going to use throughout this talk. So I invite you to think about why this map is well defined, why this is an invertible ideal in R. It requires some thinking, so I invite you to do it. And then finally, pi is the map that is used by extension. So you take an ideal in R, an invertible fractional R ideal, invertible in R, and you send it to its extension to OK. And you have to think a little bit why this map, let's call it maybe pi tilde, induce is well defined over the classes. So if you change I by an isomorphic ideal, you will get something also that works on the ideal classes. Think about it. So pi is a well-defined map on the ideal classes. And yeah, so this is everything you need to know about this exact sequence. So I invite you to prove that this sequence is actually exact. So let's say exercise. Prove that exactness. And this is quite actually a long proof because, as you've seen, several steps are required, but fortunately there are very good references for it. So if you get stuck, I invite you to take a look also at the notes by Cave Conrad. They are available online for free. And I think the title, so these notes are the notes about conductor, on the conductor ideal. If you Google it, you'll find it. Or of course you can also ask me later in the chat and in the interaction that we will have later. And yeah, so this sequence is exact. But how do we use it for computational purposes? So Okay, so we know all the ingredients, so I can erase this now. Let's stare a little bit at the sequence for a couple of seconds. So, okay, I already stated that we know how to compute it. So let me just write can compute. Cool. It turns out that the algorithm to compute the class group also give as a side byproduct an algorithm to compute the unit group for the maximal order. And again, you can use the same reference as I said before. Or maybe it's also more precise to say that there are algorithms. So sometimes they are based on the class group computation, sometimes not, depends which one do you want to use. But we can also compute the unit group here. And again, you can look into Harry Cohen's book for this part as well. Okay. So in order to compute the peak of R and the unit group of R, as I mentioned, what is missing is to understand this element in the middle. And then, using exactness and the fact that we know these maps and they are explicit, we can recover both peak of R and R star. And how this was done, the reason why we can compute this thing in the middle is that because there is an isomorphism between the quotient and the direct sum over all prime ideals of OK, the localization of the maximal order units and the localization of R at P units again. The direct sum is taken over all prime ideals, over all primes. It turns out that this quotient is 0 whenever the prime is invertible, so almost always. So this direct sum is actually finite. You only have to look at the primes that are above the conductor. So you take only the primes that contain the conductor. All the other terms are 0. And Kluners and Pauli, they have a paper about how to compute these terms. They have how to work with these localizations and hence pull back and compute this quotient, so the middle term of our exact sequence. All right, so now we know how to compute all the terms in the exact sequence except R star and pick R star, but as I said, this can be recovered by the fact that the map are explicit. So the motto, the things that I want to keep in mind is that we can compute not just the picker group of OK and the unit group for a maximal order, but also the same data for an order that is not maximal. Okay, cool. And last thing that I want to mention about computing PKR groups is that, which is quite important for us later on, is that being able to compute ideal classes gives us also to get a method to determine whether a fractional ideal is a principal ideal. So an algorithm to determine whether an invertible ideal is principal and explicitly get a generator. In other words, this means that taking a fractional ideal, which we know that is invertible, we can solve the discrete logarithm problem into this abstract group. So you can compute the image inside of the ideal class inside this abstract group and see if it is equal to the unit element of this commutative group. If it is so, this means that the ideal is principal. Since this construction is explicit, it actually gives you also a generator, the principal element. Okay. So we defined and studied and said properties about ideal classes. And now we're going to talk about a related but slightly different notion, which is called weak equivalence. So let me just say it before I forget that this notion was introduced originally by Dade, Olga Tauski, and Zassenov in the 60s. And yeah, so there is a paper from the three of them where they talk about this weak equivalence. And what I'm going to say later builds heavily on that paper. All right, so let me start by giving a proposition. So this proposition will give us like 3 equivalent statements for 2 fractional ideals I and j. So we take 2 fractional ideals, then the following are equivalent. So 1, the localization of I at some prime p is isomorphic to the localization of j at the same prime p as Rp modules. For each prime p of R. So the 2 ideals are locally isomorphic. 2, 1 sits inside the product of the inverse columns. So y is inside I colon j times j colon I. 3, I and j have the same multiplicator ring. So I colon I is equal to j colon j. And let's call this order S. So same multiplicator ring, and there exists an invertible ideal L, invertible in S, that sends I into j, or better, j into I by multiplication. So such that I is equal to L times j. All right? So definition, before I give the proof and more comments. If 1 or 2 or 3 holds true, then we say that I and j are in the same weak equivalence class. Or I and j are weakly equivalent. And we are going to use the notation I twiddle tilde weak k j. So I put this wk for weak. Okay, so this is the definition of weak equivalence. All right, and let me say, before we prove this statement, let me say a few things. So condition 1 and 2 and 3 are all particularly interesting for us, for what we're going to do, because they give different perspective of the notion of weak equivalence. So 1 tells us that this is a notion of local nature. So these two ideas, they don't need to be isomorphic globally, but they are so for every prime. So it might happen that there is no isomorphism between I and j, but locally there is always an isomorphism. 2 is very nice from a computational point of view. If you have done the exercises, or if you look at them, you'll see that it's not hard to compute a colon ideal given generators of I and j, and also the product of two ideals is quite easy to compute. It's easy to write down a function, and then one needs just to check if 1 is inside this product. So you compute this thing and you check if 1 is inside it, and if that's true, then the two ideals are weak equivalent. So it's easy to verify whether two ideals are weakly equivalent. And the third one, we are going to use it later also heavily, tells you that the notion of weak equivalence basically means that we are modding out by invertible ideals. So two ideals are weak equivalent if there exists an invertible ideal that sends one into the other, and this means that, yeah, you will see what this means later on more precisely. But now let's start with a proof. So, proof. So we are going to first prove that 1 implies 2. So we assume that for every prime there exists an isomorphism. In particular, this means that for each p, there exists an element x in the total, a non-zero divisor, of the total quotient ring of the localization of R at P, such that I localized at P is equal to x times j localized at P. Okay? So they are isomorphic, so there exists one element that sends one into the other by multiplication. Alright, now we try to prove that 1 sits inside the double product of the double colons. So let's write it down and localize it at P. So we take I colon j times j colon I, and we localize this whole thing at P. So localization commutes with product and with colon ideal. So we get IP colon JP times JP colon IP. Now we use what we know, that IP is equal to x times JP, so we write it as, so we have x times JP colon JP times JP colon x times JP. Okay, so here x is in the first, here x is in the second. Now we can pull out, if you look at the definition of colon ideals, x from this product in both cases. So here we will get x times jp colon jp, and here we get 1 over x. We already used this trick in the last video. And now we can simplify. So this makes sense because x is a non-zero divisor, remember. And so we get jp times jp. Jp is an order, so this is just the colon ideal, the multiplicator ring of jp. So when you take an order, you multiply it with itself, you get the order itself. Okay, so this means that the natural inclusion of I colon j into j colon I. So look at the definition to see why we have such an inclusion. So this sits always inside the multiplicator ring of j. So we have just proven before that this inclusion is locally at every p an equality. So it's locally surjective. And this means that it's an inequality also globally. And in particular, so this product is equal and 1 sits inside j colon j because it's a ring. So this concludes the proof. So done. All right. So let's go to the next implication. 2 implies 3. So we apply that 2 implies 3, as I said. Okay, so now we know that 1 sits inside the product of the 2 columns. All right. So observe that more or less as we said before, the product of the 2 columns sits inside j colon j. We already use it, but it also sits inside I colon I. Okay? And since 1 by assumption by 2, since this product contains 1, then these are actually equality. So this product equals j colon j, but also equals I colon I. So in particular, I colon I is equal to j colon j. Cool. Let's call this common multiplicator ring S. So we give it a name, so it's a bit shorter to write. And also, so if you look at it, so we have that I colon j times j colon I is equal to S. So this means that both these colon ideas are invertible in S and inverse of each other. So both I colon j and j colon I are invertible in S and inverse of each other. All right. Now consider the following chain of inclusions. So look at I. So since S is the multiplicator ring of I, we can also write I as I times S. Now S equals the product of the double columns. So let's expand it. So we have I times I colon j times j colon I. And now we put together this part. So we have j colon I times I, and this sits inside j by definition of colon ideal. So we have I colon j times j, and this sits inside I, again by definition of colon ideal. So we have I equal included in I. So I included in itself. This means that all this chain of inclusion are actually equalities. And in particular, this means that we have that I is equal to I colon j times j, which is this part here, so we have equality. And we also just said that this is an invertible ideal, so this is going to be our L from the definition of free. Great, so this concludes this implication. And for the last implication, that's maybe the easiest. So we know that there is an invertible ideal that sends I into j, or maybe j into I. And we want to prove that there exists a local isomorphism. And the trick is just to remember that invertible ideals are locally principal. So there is a little step here. Let me explicit down. So we are localizing at a prime ideal, a prime of R, but we are looking at an ideal over S. So we take a prime in R, and we observe that when we localize S at P, so at the multiplicative set consisting of all elements of R not in P, this is a semi-local ring. It's not local, it's semi-local. So there are only finitely many maximal ideals in here, which are precisely the primes in S which contain P. And nevertheless, we have seen yesterday in what I think was called lemma 1 or maybe lemma 2, I don't remember, that an invertible ideal also over a semi-local ring is principal. So not just local but semi-local. And in particular this tells us that the localization of our invertible ideal that we have, because we are assuming free, is principal. So there exists an element x, non-zero divisor, such that the localization of L at P is equal to x times SP, this semi-local ring. And now observe that IP by assumption is equal to LP times JP. So we know that I is equal to L times J. We localize it at P. And now we use what we just discovered, that L is principal, LP is principal, so we get x times SP times JP. And now we use that S is also the multiplicator ring of J. So this becomes x times JP. So we have IP equal to x times JP, which means that they are isomorphic. We have a non-zero divisor that sends one into the other. IP isomorphic to JP, which is what we wanted to prove. And this concludes this implication, and in particular the whole proof of the statement. All right. So we have defined the notion of weak equivalence. As the name suggests, it is an equivalence relation. It's very easy to prove it using 1, 2, or 3. I invite you to convince yourself that that's true. And this means that we can form the set, we can form the quotient, we can mode out by this equivalence relation. And we're going to give it a name. So we're going to denote it by W for weak. So W of R is going to be the set of fractional R ideal, I of R, modulo this notion of weak equivalence, which, as I said before, I'm going to denote it by this tilde WK, weak equivalence. Weak equivalence. All right. And since we are defining things, let me also introduce a bit more notation. So for every overorder of S of R, we denote by W, R, and we put an S here, so Pelix S, the subset of the fractional array ideals with multiplicator ring equal to S. We take all fractional array ideals, but we require the multiplicator ring to be equal to S. Okay, and again we mode out by weak equivalence as before. Observe that by condition 3, two weakly equivalent ideal have the same multiplicator ring. So this makes sense, it's well posed. This definition is well posed. Okay, so we already seen the definition of the ideal class monoid, and now we just do the same trick also for the ideal class monoid. So we denote by ICM of R with a predix S, the fractional R ideals with multiplicator ring equal to S, modulo isomorphism this time. So this is the ideal class monoid of the subset of the ideal class monoid consisting of the classes with multiplicator ring S, and which is similar to what we did here. Okay, and also this one is well posed by the lemma that we have seen in the beginning. So the multiplicator ring is an invariant of the ideal class. So it is all good, no problems coming from here. Okay, before we move on, let me just say another property of weak equivalence that turns out to be very handy. And actually something that we can deduce from the proof that I spelled out, but it's good to have it written in a statement so that it's more clear. So I'm going to state it as a corollary. Okay, we assume that we have two fractional ideals I and j which are weakly equivalent. Then we have that I is equal to I colon j times j, and I colon j is invertible in the common multiplicator ring. So this should appear in the proof, so there is not just that I wanted to stress it. But also that if this is the case, so if we have two fractional ideals that are weakly equivalent, we have that they are isomorphic if and only if this invertible ideal I colon j is principal in S. Okay, proof. So one, there is nothing else to say. We already seen it in the proof of the previous proposition, so I'm not going to say anything more. Two, let's give one implication. So say that we have an isomorphism between the two, so we know that there exists an element x that sends j into I. Right? We can write this product also as the product of the principal ideal generated by by x times j. Right? This is the same because S is the multiplicator ring of j. And now observe that I colon j, so this is equal to x times j colon j. We can pull out x, and this becomes x times j colon j, which is equal to xs. So this ideal is actually not just invertible but principal. All right? And for the other direction, if this ideal is principal, then well, you just plug in the generator in this relation and it's done. So the other direction is trivial. Okay. So why this corollary is important? So as I said before, the computation of the picker group allows us to determine whether an invertible ideal is principal. Whether an invertible ideal is principal, but also computing the picker group allows us to determine whether two invertible ideals, both invertible in the same ring, are isomorphic, because you just pull them back into their class inside the picker group and you check if the class is the same. But for non-invertible ideal, a priori we didn't have a method to check whether they are isomorphic or not. But this corollary together with the proposition gives you an algorithm, right? So first you take two fractional ideal. In order to be isomorphic, they have to be weakly equivalent. Think about it. And if they are weakly equivalent, then they are isomorphic if and only if this ideal, which is invertible, is principal. And we know how to check whether this ideal is principal because it's invertible. We just pull it back inside the picker group of S and you check if it gives rise to the trivial class. Okay, so the motto of this part is that we can computationally check whether two ideals are isomorphic, both in the invertible case and in the non-invertible case. Great. All right, so we have studied this notion of weak equivalence. So now we move on to another computational problem that it's good to have solved in order to compute the ideal class monoid. So that we need to solve in order to compute the ideal class monoid. And this is the problem of determining the overorders of a given order R. Okay, so we have on our order, well, if the order is maximal, there is nothing to do. The only overorder is itself, so the problem is trivial. So we're going to assume that the order R is not maximal to our trivialities. And we have a natural bijection between the set of overorders of R and the subrings of the maximal order of the Thal algebra modulo R of this quotient. And observe that since both OK and R are lattices in K, this quotient is finite. So this proves you that there is only finitely many overorders of R. So if it is not clear to you, just think about what is this bijection. So you just take an overorder, let's say S. So this is something that is a ring that contains R and it must be contained in the maximal overorder by definition. And you send this S into, well, the class in the quotient of, well, S plus R. Let me use additive notation. Let's use additive notation. But observe that S plus R is equal to S because R is contained in S. So this is a bit, okay? So maybe let's write like this. Right. Okay. So this is a finite problem. This is a finite quotient, and we need to find other orders. So one naive thing that one can do is to just look at this finite quotient, find all the subgroups, and lift them to modules, to our modules. Check which one are closed by multiplication by R, lift them, and see then which one are orders. But this method is incredibly inefficient because even in very simple cases where the Thal algebra is small dimension over Q, this quotient can be actually quite huge. It depends on the order R, and the order R can be very far away from the maximal order. So the lattice of overorder, the inclusions of this overorder can be a huge tree of inclusions, and this will make this process very, very slow. There are many, many subgroups of this thing that are not subrings, so it will be very inefficient. So a much better way to do it was found by Tommy Hoffman and Carlos Circana. In 2020, they have a paper where they found a much better method, and I'm going to give you a sketch of their idea. So the idea consists in first it's enough to find minimal overorders. why it is enough. So find minimal overorders. So we start by finding the minimal overorder. So minimal means that it's a overorder strictly bigger than R, but there is nothing in between. There is no other ring between the two. And this is enough because then you just iterate. So you find the minimal overorder, you find the minimal overorders of this one, and so on until you find all the orders. So you just find the one of R and then you iterate. So this is enough. And the cool thing is that minimal overorders are easier to find than general overorders. And the reason is that, so the minimal overorders are, by the bijection that we have just shown, all sent to subrings of the quotient of the multiplicator ring of a prime ideal P modulo P, where P is a prime ideal above the conductor. So prime of R containing the conductor. Okay, and why is this much better? So the conductor, containing F, the conductor, R over, okay, we have already encountered a couple of times. And why this quotient is much better than the quotient over there? So, okay, modulo R was just a finite quotient, but it's a priori a finite group. It doesn't have a very nice structure. While this P colon P modulo P is a quotient, has the structure of a module over R modulo P. It's a module over R modulo P, and P is a prime, so it's a maximal ideal. This is a finite field. So this is a vector space. It's a vector space over a finite field, and also it's finite. So it's a finite dimensional vector space over a finite field. In other words, we can use linear algebra to find the minimal overorders, and this is much, much faster than considering subgroups. So it's not just much smaller than the quotient, but it's also like much better handled from an algebraic point of view. So we can use linear algebra. Over finite fields, which is very fast. Okay, so the motto from this discussion that I want you to keep in mind is that we can compute overorders. So we have a good algorithm to solve this problem. Okay, now let's move on. I defined the notion of weak equivalence. I told you that it's easy to check whether two ideals are weakly equivalent. And then I defined the quotient W of R of the set of weak equivalence classes. And now I want to tell you how to compute this W of R. All right, so first of all, observe that W of R equals, so there is a partition into the sets Ws of R. So we can partition by multiplicator ring when S loops over the overorders. Okay, so the multiplicator ring is an invariant of the weak equivalence class, so this makes sense. Okay, I just told you how to compute the overorder, so we are not worried about computing this set here. And this means that it's enough to compute Ws of R. So if we can compute all these sets, then we can compute WR by just putting them all together. So proposition. So this proposition is going to tell you how to compute each of these sets. So take I a fractional ideal, R ideal, and assume that its multiplicator ring is some S, some over order S. So something whose weak equivalence class will lie into this set here. And then let T be an overorder of S such that the trace dual ideal of S extended into T is invertible in T. So this sounds, okay, where is this coming from? You'll see it in the proof why this is the right notion. Okay, so we take the trace dual of the order. We have seen yesterday the definition, and if you have done the exercises, you know that it's not too hard to compute it. It's actually quite easy and efficient. It's just a matter of linear algebra. And then you take this ideal, you extend it to T, and you require this T to be this extension to be invertible in T. So let me stress one thing: there exists always such an order T. Because if you take, for example, T to be the maximal order, then you will have that ST times OK is an ideal of OK, and every ideal of OK is invertible. So this thing will be invertible. So there exists such a T. But for efficiency purpose, I'm going to say it again later, we want T to be as close as possible to S. OK? And then let F be a fractional ideal, well, of R a priori, a fractional R ideal, such that satisfies the following two conditions. So it is inside S, and T is contained in the multiplicator ring of F. All right, I'm going to say more about this ideal before we start with the proof, but then let me just conclude the statement of the proposition. Then there exists an ideal J. So this is a fractional ideal such that J is in the same weak equivalence class of I. Okay? And 2, J sits between this ideal F and the order T. Okay, so let me say a few things about this statement and then we're going to prove it. So remarks. So one is something that I already said. We can take T to be the maximal order. So such T exists. So OK satisfies the condition that the order T needs to satisfy. We can also take for the ideal F the colon ideal, the relative colon ideal. So S colon T. So also there exists an ideal that satisfies the condition that F has to satisfy. But the proposition tells us that every ideal will have another representative in the same weak equivalence class that lives inside between F and T. So in other words, we can find all the representatives of all weak equivalence. We can find our representative of all weak equivalence classes in the submodules of the finite quotient T over F. So let me write it down. Can find the representatives of W small s of R among the lifts of the sub-modules, sub-S modules of the finite quotient T modulo F. Okay, let me say a few words about it. So the submodules of this finite quotient are in one-to-one correspondence, they are in bijection with the S modules that contain F and contains T. This is the definition of a quotient, basically. So for computational purposes, we want to keep this order as small as possible. So taking T to be the maximal order is a bad choice in general. So if we can find a T that is smaller than the maximal order, it's much better. This quotient will be kept a lot smaller. So this is what one wants to do. Keep this guy small. Okay? Let's prove this statement. So it's one of these statements that sometimes the proof is easier than the whole statement itself. But still requires a few steps. Okay. So first of all, so let T be and is in the statement. We have that the map, the natural extension map from the picker group of S to the picker group of T. So this is the map that takes a class of an ideal, we multiply invertible ideal in S and it sends it to the extension in T. So this map is surjective. And the reason is that we have a commutative diagram of surjective map that goes to the picker group of OK. If you think about it, this proves that this map is surjective. Nothing else to say. And these maps are surjective because of the exact sequence that we have seen before. So we already knew it. OK, first consideration. Then second, remember that having multiplicator ring equal to S, so for I to have multiplicator ring equal to S, is the same as requiring I times IT, the trace dual of I, to be equal to the trace dual of S. So we have seen it in a lemma in the last video. And this implies that since the extension of ST to the order T is invertible, the same holds true for the extension of every ideal with a multiplicator ring S. Think about it. All right. Now, let me give a name to this map. We're going to call it pi. Yes, now we're going to want to work with it. Now, let's define an ideal J prime, to be the representative of the class corresponding to the pre-image of the ideal T colon IT. So we know that IT is invertible in T. We take the inverse. And then we pull it back by the map pi that we have just defined. Okay? So we have defined this representative J prime of this particular class, which corresponds to the inverse of IT inside T. Now, define the ideal J as the product of I, so the one that we started with, times this J prime. Observe. This J, so defined, is weakly equivalent to I, because J prime is invertible in S. Right? It's the preimage of something invertible via surjective maps. So a surjective map from a picker group to the picker group. So it is invertible. Let me write it down. So J is weak equivalent to I because J prime is invertible in S. All right, and moreover, J extended to T equals T. So we have this relation, which now we are going to exploit to deduce that J is containing T and contains this ideal F. All right, in order to do so, okay, first of all, observe that by definition of colon ideal, J sends T inside T. So lives in the colon ideal T colon T, which is, since T is an order, just equal to T. All right, so we have one of the two inclusions that we want to prove. And for the other one, observe the following. So take the product F times J and write it as F times T times J. So why this is the same? Because T is contained in a multiplicator ring of F. This is one of the assumptions that we had on this ideal F. So this means that F times T is equal to F. Okay? So we can add a T in the middle of this product. Now we put this thing together and we have just proved that this is equal to T. So we get F times T. And this is equal to F. So again, let me write it down what I said, that these two equality hold because T is contained in a multiplicator ring of F. All right? And then, for the last line of the proof, we have that since, by assumption, F is contained in S, which is equal to the multiplicator ring of I, which is also equal to the multiplicator ring of J, because I and J are weakly equivalent, then we get, from what we just proved, that F times J is equal to F, we get that F, J, which is equal to F, as I just said, sits inside J. Okay, so F is contained in J, which was the other inclusion that we wanted to prove. F inside J and J inside T. This concludes the proof. All right. So the meaning of this statement, that is the thing that I want you to keep in mind, is that we can compute the weak equivalence classes of a given order by writing it as a partition over the weak equivalence classes with prescribed endomorphism ring, prescribed multiplicator ring, and then this proposition tells us that we can find a representative of this subset inside a finite quotient. This quotient is finite, so this means that we can find all the representatives. We just lift all the submodules and then we mod out by weak equivalence. We take only one representative among these sets. And we have seen in the very definition of weak equivalence that it's easy to check whether two fractional ideals are weakly equivalent. You just need to check if one is inside the product of the double column. Okay, now we are ready for the final step. So how to compute the ideal class monoid of an order. So we know how to compute the weak equivalence classes, and now we want the isomorphism classes. section, compute ICM of R. So I said it, let me write it down so that it is even more clear. So we can compute WS of R for every overorder S of R. Okay. Theorem, which is going to be the recipe to compute the ideal class monoid of R. The natural action, so the action induced by multiplication of the picker group of S, of one fixed overorder S, on the set of isomorphism classes of fractional R ideal with prescribed multiplicator ring S is free, is a free action, and the quotient by this action is equal precisely to WS of R. So the set of weak equivalence classes with multiplicator ring S. Oops. Okay, so you take the set of isomorphism classes with that prescribed multiplicator ring, you mod out by this action of the picker group, and you get precisely the weak equivalence classes. So let me just say what this means for us. Hence, so if I1, I2 up to IS is a set of representatives of the weak equivalence classes with multiplicator ring S, and if J1, JR is a set of representative of the isomorphism classes in pick of S, so the invertible fractional ideals invertible in S, then the set consisting of all the possible products coming from these two sets, so let me write, I call II and JJ, so indexes. So for I that goes from 1 to S, and J that goes from 1 to R, is a complete set of representatives of the isomorphism classes with multiplicator ring S. So ICM S of R. Okay? So we know, as I said before, we know how to compute this guy. We know how to compute this guy. So in other words, we have explicit sets of these representatives. We just take all the possible products, and this is going to give us the ideal class monoid of R with restricted multiplicator ring S. Okay, let's prove it. So proof let's prove that the action is free. Okay, we pick classes. So we pick an isomorphism class of an invertible ideal J, and then we pick any fractional ideal I with a multiplicator ring S, and we take its isomorphism class. Okay, we want to show that the action is free. So this means that we want to show that if I is isomorphic to I times J, then J is isomorphic to the trivial isomorphism class. So it's isomorphic to any principal ideal, or it's a principal ideal, which means isomorphic to the order S. Okay? So, first step, by modifying this J within its own isomorphism class, so we just take a different representative, we can assume that instead of having just an isomorphism between I and I times J, we have an equality. So we reduce our proof, we are reduced to prove that if I is equal to ij, then j is equal to s. Okay? So instead of working with isomorphism, we can work with equality by just tweaking the representative of the isomorphism class of j. And this is, so in order to prove this implication, we will do it locally. We will work locally. So we localize at a prime P. Right, so our equality becomes an equality of the localization. So remember that J is invertible. Invertible means locally principal. So we have that there exists X non-zero divisor such that J localized at P is equal to X localized at P. X times localized at P. So the equality that we have just written when you localize becomes IP equal to X times IP, right? So X sends IP inside itself by multiplication. And this implies, by definition, basically, that X lives in the multiplicator ring of IP, which is SP by assumption, because I is multiplicator ring S. But observe that you can do the same trick when you divide by X, because X is a non-zero divisor. It's a generator of an invertible ideal, so it must be a non-zero divisor. So in the same way, you get that 1 over X lives in SP. So this means that X is a unit in SP. Okay, and this means that the ideal J is generated by a unit, so it's equal to SP. JP is equal to SP. Right, and it's what we wanted to prove locally. So we wanted to prove that J is equal to S, and this is true locally. But this argument works for every prime. So X is going to depend, it's going to be a local generator of J at P, so it depends of P, but then it kind of disappears from the equation. Right here there is no X. So this means that this is true globally. Right, so we prove that J is equal to S. Okay, so this means that the action is free. Therefore, the action of pick of S on the isomorphism classes with multiplicator ring S is free. so as claimed. All right? And now, to conclude, we just need to show that the weak equivalence classes with prescribed multiplicator ring S is precisely the quotient of ICM S of R by this action. But this is something that we already know. So observe that W S of R being the quotient by the action by multiplication of invertible ideals of S is just a fancy way to write condition 3 of the definition of weak equivalence. So actually there is nothing else to prove. We are done. Okay. So this means, so the meaning of this theorem is that we can compute the ideal class monoid of R with prescribed multiplicator ring S. And so let me just write the concluding steps. Conclusion. So we have an algorithm to compute ICM S of R from the knowledge of WS of R and pick of S that we know how to compute. And this means that we can compute the ideal class monoid of R, because remember that this guy partitions into this kind of sets, into ICM R of S, where S runs over the overorders. Right? So we loop over all the overorders, we compute these sets using the theorem, and then we put together all the representatives, and we get representatives of the ideal class monoid of R. So the motto is that we can compute ideal classes of an order even when we consider the non-invertible one. All right? So this concludes the lecture. Let me just say 2 words. So about the speed of this algorithm. This algorithm works in practice. It's a finite algorithm. For theoretical reason, it will finish eventually. But as you have seen, probably as you figured it out, the bottleneck is to compute representatives of sub S module into the quotient T modulo this F that we have seen in the proposition of the weak equivalence classes. Sometimes this quotient is huge, is too big. We cannot just like brute force it and find all the representatives. So the algorithm works, but in certain cases it's just too slow. So it might not work. So there is room for improvements if you want to think about it. I think have fun. All right, this concludes the video.